Okay, so back to the emission spectrum, which is where we left off in the last video. And in the last video, right at the end, I was saying, like when you put that, so the emission spectrum is the light that's given off when you take a gas of any element and you heat it to the point of incandescence, to the point that it gives off light. And then you look at that light through a prism. And we have what are called spectroscopes. And the spectroscope is just kind of like this viewing apparatus you put to your eye, but inside it has a prism that breaks up the white light into its colors. And so you'll see then like a dark strip with a series of lines that are different colors. What colors depends on which element you're looking at. So if it's hydrogen we're looking at, we'll see 4 lines. Purple, blue, green, and red. And the green one's really, 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 really dim. You can hardly see it. It was one of the limitations in Bohr's model. So when you break the light up into its colors, purple, blue, green, and red, when you look at just the color with your naked eye without the spectroscope, you see the color that the tube gives off is like a purple pink. And it makes sense when you think about the 4 colors being emitted here. The green's really weak, so you have a purple, a blue, and a red, and when you mix those together, you're going to get a purplish pink color being emitted. If you look at the neon tube is my favorite. It gives off this bright orange neon light to our naked eye, and when you look at it through the spectroscope, you see like 20 orange lines all together down here. They're just like phenomenal. And then there's a few red and a few yellow and a couple of green. And that's it. There's nothing else on the blue end of the spectrum, the purple end of the spectrum. So it makes sense that then the overall color of the light that the neon tube gives off would be an orange. Okay? So the color of the light that's being emitted then gets broken down into these component colors by the spectroscope, the prism. And I said like hydrogen was red, green, blue, and purple. And so the more and more people look at these, then it can become like a game. You put one in and you say, okay, who can guess which one this is? And so if it's purple, blue, green, and red, then it's like, oh, it's hydrogen. If it's one that has a whole ton of bright orange and not much beyond or nothing beyond green, then it might be neon. If it's 2 solitary yellow lines, it's probably sodium. So the emission spectrum for a given element is unique for that element. And elements can be identified by their emission spectrum just like we can be identified by our fingerprints. Okay? Now, it's not that the light that, like I said, sodium was just 2 yellow lines. Remember, these lines that we are seeing are a result of the light being given off in the visible range. So there could very well be ultraviolet light being given off down here and infrared light being given off up here, but obviously we can't see them. And so labs that do spectrometry, they would have like computers hooked up to their spectrometers so that the computers could sense the higher and lower frequencies. But if we're just doing it with our eye, we're only going to see the visible. Okay, so everything in between these lines of light that we see is black. It's darkness. And when you look at an emission spectrum, you need the room to be pretty dark. You need a little bit of backlight so you can see, like lots of spectroscopes have like a number scale, so you could read the wavelength off here. So if that's the case, then you need to be able to see that scale. But you don't want other light in the room because the other light in the room will be picked up by the spectroscope too. Okay, so it's bright lines and all the rest is black. And because of that, the emission spectrum is often called the bright line spectrum. Seems to make sense. Okay, now what's happening? Well, what's happening is these lines of color that we are seeing are matching the photons being given off as an electron falls from a higher level to a lower level. So we said it happens when a gas is heated to the point of incandescence. So when you heat a gas to the point of incandescence, what you're doing really is you're causing all the electrons to get excited and to jump up to a higher level. But they're kind of like little kids. They don't like being up there for very long. Like little kids want to go to their friend's house for a sleepover and then they stay like an hour and then they want to go home. So that's kind of the same with the electrons. They don't stay an hour. They don't stay very long at all. And then they fall back down. And we know that when they fall back down, they emit photons of light. If those photons that they emit end up being in the visible range, then we see a line of light in that spot. Right? And so the photons they emit are going to be different wavelengths depending on which levels they're falling from. So something falling from a 2 to a 1 will have one wavelength, where if it's falling from a 3 to a 1, it'll have a different wavelength and result in a different line on the spectroscope. They could also fall from 3 to 2, right? So you can get all these different lines. So what would happen then, you would find the energy of these photons, find their frequency, switch it into wavelength, and see if it falls in the visible spectrum. And then those are the ones that you should see. Okay, so that's the emission spectrum. And remember, they're like fingerprints. No two elements can have the same emission spectrum. The other spectrum is the absorption spectrum. And I had said, I had said in an earlier email that it is like the twin or the mirror image of the emission spectrum. Okay? What we're going to see here is the absence of the lines. Okay, so up here it was all black except for bright lines. Here what we do is we take a gas, and it's a whole different setup, but we take a gas and we shine light of all wavelengths on it. Okay, so this is light of all wavelengths that we're shining on it. And then we look at the light that comes out with our prism. Okay, so here's my spectroscope that has the little prism inside. We look at it, and what we'll see, the absorption spectrum then, will be the full spectrum of light that we've shined in, but in spots there will be dark lines. There will be color missing. And the dark lines, the color that's missing, will be the photons that have been absorbed to jump the electrons up. So up here it's black with the colored lines that's being given off. Down here it's like the rainbow with the dark lines in the spots of the photons that have been absorbed. And that's why it's like the mirror image. This one, yeah, perhaps no surprise, is also referred to as the dark line spectrum, because what you see are the dark lines representing the photons that are missing. Okay? And again, just like that one's unique for every atom, so is this one. The one last piece then before we move to our next model is the hydrogen atom for a minute. Because Bohr did so much work with hydrogen, we know that hydrogen has, we know 5 different series. Now, it could be that there's more but I don't think so. So 5 different series of lines. And they were studied during Bohr's time and a bit beyond, and then they were named. So I want you to think then about, so here's n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. And it's not an accident that I'm making the ones as you go up closer together, because that is the truth. So the higher you go, the closer the lines get together. And the biggest drop is from the 2 to the 1. Okay, so we have 5 different series. The first series is called the Lehman Series. And the Lehman Series is when photons fall from any higher level down to n equals 1. Okay, so when a photon falls from anywhere above down to n equals 1, you get the Lehman Series, and these guys are in the ultraviolet part of the spectrum. So we can't see them, but our computer can detect them. Okay, so that's Lehman. The next series is Balmer. And Balmer are any photons released when electrons fall from a higher level to an n equals 2.